So here we do a material frame indifference. Yeah. Axiom on material frame indifference. And it sounds a little bit difficult, but not so difficult actually if you understand the concept. So let me see. Let me go to YouTube. You can see my channel live. It sounds a little bit difficult. I think it's working. So I copy this and I put here. It's 204. It's 204. Okay. So 204. I make things same. Here and here same. Okay, so this is not working. No. We discussed the motion of a continuum with respect to coordinate system fixed in space. In classical mechanics, we consider the Newtonian idea of absolute space and absolute time and observer with a measuring tape and clock for everyday engineering application, including trips to the moon and beyond. This approach has worked out satisfactorily. When the physical properties of material are to be determined, we should know how the motion of the observer will affect the measurement. When the physical properties of material are to be determined, we should know how the motion of the observer will affect the measurement. Although the values of measured quantity may depend on motions of the observer, their interrelations must be independent of the observer. For example, the velocity and acceleration of particles would appear differently to different observers moving with their own velocities and acceleration. However, the distance ds of the particle covers in time dt must be independent of the observers. I'm not sure about this. The distance ds the particle covers in time dt must be independent of the observers. Quantities that are invariant under observer transformation are called frame indifferent. Other terms for this concept include objectivity and observer independence. An observer transformation is defined as this. See, I think I explained this. This is a trajectory of frame. So if you have frame like this, see, x, y, z, then you have another frame, maybe x, y, z. So this is called x prime, y prime, z prime, and this prime coordinate is actually moving like this. See, by b, t. At the same time, this coordinate is rotating by Qijt. Yeah, I think this is it. Anyway, where x and t represents an absolute Cartesian system of coordinates, and time, as in classical mechanics, the observer's coordinate system x prime is translating and rotating as a function of time. The observer's coordinate system x prime is translating and rotating as a function of time. The rotation matrix Qt is orthogonal. The distance relation is this. The distance, if you want to see some distance in space, for example, some distance, you have 2 points, this one, this. So you can call this distance as ds. And distance is the same in terms of either coordinate system, primed coordinate system or unprimed coordinate system. The distance is the same, right? Thus, the absolute distance and distance measured by the observer are identical. And it is useful to note that this orthogonal matrix transpose times orthogonal matrix is one identity. So by differentiating both sides, we obtain this one. We obtain this one, right? By differentiation, including constant shift in time, tau prime equal t minus alpha. We define two motions, xi prime, xt prime, and xj, xt as object. We define two motion, this and this, as objectively equivalent if first one is the second rotation of second one and translation. The relation between velocities, you can see you can take time derivative and you can obtain the velocity in primed coordinate, which is given by this. And this shows that velocity components are not frame indifferent because you have this extra term. If you don't have this extra term, this is frame indifferent. Or objectively equivalent. Objectively equivalent. I think this is a frame indifferent. frame indifferent. Differentiating again, we have this acceleration. We have acceleration, which is again not frame indifferent, because we have these two extra terms. If we didn't have these extra terms, this is a frame indifferent. An objective tensor would follow the transformation law for tensors under objective coordinate transformation. An objective tensor would follow the transformation law for tensor. Okay, here we have a break. An objective tensor would follow the transformation law for tensors under objective coordinate transformation. That is, Aij is objective if you have some tensor Aij, which is a function of t prime, if it can be written as this way, where functions are where the things are function of t, then this is called objective tensor. If this is satisfied, this is objective tensor. Using a relation, okay, so this guy is just consider rotation, because okay, if you have dx, if this is dx prime, then if you have dx, this transformation is just a rotation, The relative translation doesn't matter. Where you find this piece doesn't matter, right? You just consider rotation to find the relation between these. Then we can write the velocity gradient, which is not objective as. Yeah. So this is also something, you can see. I think I wrote this somewhere, right? So Vij is Qij this way. QijV this is more like identity thing. See, you have this one. This part is XL partial XL. This is 1. So you just inserted 1 in some place. The second one is you just directly Vj. Vi prime is Qij. Vj plus q dot ij. I don't remember. q dot ij xj xj, then b dot t. Is this t or t prime? b dot t. Yeah. xj. This is xj. So this is xj. So the first term becomes, sorry. So then you take partial derivative like this. So the first term becomes like this. Second term becomes like this. Just take this part is the partial derivative of this. Then this is not a function of kx, k prime at all. This is just some arbitrary translation. So this will be deleted if you take a derivative, partial derivative with respect to x k prime. So you obtain how do you obtain this? This part, see? This part is this one. Is it complicated? X prime was like qx plus bt, right? So partial x prime is, actually I think what we should is this. Partial x equal q partial x and plus 0, right? So, and this is more or less 1. No? It's so complicated. X, okay, here you have x. Yeah, if you partial j, partial k, for example, prime, if I use, so this is qijt partial xj partial xk prime, then this will be deleted, right? So then, yeah, partial, you just differentiate partial L. So what you get is partial L, partial K. This is not identical. How do you say this is identical? J, K, J. So hard to see. So this is like identity matrix, right? You know, this side is identity matrix, IK, in terms of IK. So that means partial xj, partial xk prime is q ij, ij transpose. That means qji. So this is qji. QKJ, QJK, QJK, QJK. You see, QJK. But it is KQ. It's so hard to follow. So hard to follow this. Let me try to work out in my note. Then I will show you the result in the next video. Okay.